Welcome to the to lecture 14 of thermodynamics of materials. One point I actually tell you, this is lecture 14, and last day I think it was extended lecture 13. Call it actually it was extended class lecture 13 because it has made up the lost time. Okay, in the previous some previous classes, you remember some of the classes were actually curtailed because of technical difficulties. So that has been made up in lecture 13. So it remains one class. So lecture 13, and today is lecture 14. Another point is assignment 1. Last class I said due date this 29/1/2023. It was incorrect. It would be 20 yesterday's date. What is that? 27. Yesterday date is over and it is April 4. This is already over. Already discussed. Yes, come on in. Discussed yesterday. Note this. So assignment 1, due date was wrong. We correct this, 27 is voltage. Next, today we start with, again we are back to last heat capacity. Back. Heat capacity. We will consider heat capacity of gases, ideal gas, real gas, liquid, solids, but not in this sequence, but maybe actually haphazardly. So, for example, I start from ideal gas, which will be easiest. Ideal gas I consider maybe number 1, and this is first. Again, there are divisions. Monatomic, okay, A. Monatomic. You remember this? Monatomic means say inert gas. Again, start. What is the internal energy? Recall. Monatomic means N is 1. Recall is 3 and degrees of freedom. So 3 translations. Okay. U translation. You recall. U translation is what? Come on. 3/2 kT. Recall this. 3/2 kT per molecule. Note this. And it is 3/2 RT per mole. Mole means gram mole. So if you have doubt, mole is gram mole, and 1 mole contains Avogadro's number of 1 mole contains n molecules. 1 gram mole contains Avogadro's, N is Avogadro's number, okay, as you know. I already gave you Avogadro's number. Come on in. Avogadro's number, okay, this. So remember this sometimes, okay. 1 gram mole, 1 gram atom. For gram atom, we use gram atom. For gram mole, we might use 1 mole, okay, or 1 gram mole. So per mole. So Cb is what? Heat capacity is our discussion. Cb is what? Del U, del T at constant volume. What is this? Del T. What is U? 3/2 RT at constant volume. Right? Volume does not matter here. Okay. It can be actually total derivative as well, not partial derivative. No significance. This is total derivative as well. So what is this? 3/2. This Cb. Heat capacity at constant volume for monatomic ideal gas. What is Cp? Cp is, you remember, what is this? Del H, only yesterday. Del T at constant pressure. Now what is H? You separately do this here. H is what? U plus Pv. U is already 3/2 RT. So 1 mole I am talking of. And then Pv is 1 mole ideal gas nRT. Means N is 1. 1 gram mole, so RT. So it is 5/2 RT. So you use as the del T of 5 by 2 RT constant volume does not matter is 5 by 2 R. These are the two heat capacities for monatomic ideal gases like helium, neon, etc. Inert gases, argon. So now, so this gives you what? This what gives you Cp minus Cv is R, just R. The quick way to deduce, quick way to derive this. But I will give you actually detailed derivation later on. So this is the monatomic. Diatomic, next is diatomic. What is this? So let me start with this B diatomic. And diatomic, that is N is 2. N is 2. So you have 6 actually, remember? Of 6, U is what? Tell me. U translation. You start with U because you want to get to Cv. So by differentiating. So get U first. So U already done. So I am repeating it as if U translation plus U rotation plus U vibration. Okay. So what is this translation? 3 moles. Remember 6 is what? 6 is what? 3, 2, 1. 3, 2, 1. 3 translation. 3 by 2. Again per molecule I am writing as if per molecule. U per molecule I write per molecule. Per molecule 3 by 2 kT. This is 3 by 2 kT. Okay, 3 by 2 kT. What is this? Again 2 moles. 2 moles. 2. It is 3. This is 3. This is 2. This is 1. 6. Total 6. So 2 is 2. Again half kT each. Half kT each. So kT. Plus vibration. Plus U vibration. Let me write this way. Better. Sometimes we ignore vibrational internal energy, but why I will explain. So what is this? 5 by 2 kT plus U vibration. Remember, U vibration is a little bit complicated because it is actually explained by quantum mechanics. Because this is quantized. This energy is quantized. Means there is forbidden energy gap. Means not all energies are accessible. Difficulty, not continuous. So that's why we have to consider quantum mechanics or quantum theory. So for this, can I go up? So from this point, remove this. Can I remove this? Remove this. Remove this. So 5 by 2. So what is U then? Once more, I am writing. Then start from below. 5 by 2 kT plus, you know, this is quantized value. I gave the value. Anyone remembering that value? I gave you in the class. H nu by e to the power exponential H nu by kT minus 1. This is the expression. So it is quantum. Okay. H is a Planck constant. This I already gave. Nu is the frequency of vibration. Frequency of H is a Planck constant and T is the temperature. Okay. Remember this. So this is the expression. So Cv is what? Do yourself. Del U, del T at constant volume. Happy? So what is this? 5 by 2K first term. 5 by 2K plus what this? Do with me. H you take a ddt of this. ddt. You see? Sukanto, ddt of this. ddt. Ct is showing here. So first you do this. H nu. Then ddt of this 1 by means minus 1 by x square. So do that. So give a minus here somewhere. Minus. Minus. Minus can I? Plus. Okay. So can I minus? Well, keep it plus. So minus heavy maybe. Yeah. Minus. Give a bracket, then no problem. Yeah. Minus what? Oh, it is better right here. Minus here is better. 1 by right nicely. 8 to the power kT minus 1. The 1 by minus 1 by x square. Okay. So square. First of all, 1 by x minus 1 by x square. Very good. then differentiation of this itself, that is times, okay, times, okay, this e to the power mx. Second, again, what is this? First, it will h nu by kt will come back, and then the dt of 1 by t, you have to minus 1 by t square. Is okay. This is okay. See, the dt of h nu by kt, the dt of this, the dt of this. Okay. Happy? The dt on the dt of e to the power mx. E to the power mx is e to the power mx first times d dx of mx. D dx of mx means m. Here d dt of 1 by t minus 1 by t square. I think correct. So first of all, this minus and this minus easily cancel out. So little bit of rearrangement. 5 by 2k. 5 by 2k. Do this. What will do? Okay. Okay, t square. Wait a bit. I think I have to. Have I made any mistakes? Mistake here. E to the mx is e to the mx times not the dx of mx means m. Okay, so m is what? This, okay, h nu by k. There should be h nu by k. H nu by k must be there. Okay, this is first of all. Then the dt of this. The dt of this is what? H nu by k, and then of course what I have written already. This must be correct then. So do one thing. Look, this h nu. So h nu by k, I am giving this h nu by k. H nu by k, I am writing this is by k, this is by k, so k times, you take a look, this is correct, divided by e to the power h nu by kt minus 1 squared, and then what remains? E to the power h nu by kt. You please check this. Check, I am helping you. This term is, oh, sorry, this is here, and this is here, okay? So I am working on this. H nu, I divide this by k and multiply by k. So k by k twice, appearing 2 times, so squared. Okay. So this can I write this way? 5 by 2 k plus k. I am writing this way. This is maybe u square e to the power u minus 1 squared. Take a look where u is h nu by kt. I made a mistake. Oh, I have not absorbed t square. You have not noted that. H nu by k, h nu is double, and t square is also squared. So it should be best. Take a look. T square was outside. So include this. Easy, very easy. Very easy. Take your time, you will see this. So u square e to the power u, u square e to the power u minus 1 whole square. Where u is k is there. Again, from this you work on the top. I remove all these things. So what you get? I'm writing u still k common. K can be common. 5 by 2 plus u square e to the power u minus 1 squared. Okay, happy? This is answer. This is the u. Oh, sorry, CB. Oh, CB. I'm very sorry. CB. Okay. This is for how many? How many molecules? 1. So K is showing. K showing means 1. Okay. K showing means 1 molecule. Return this. This will be useful. Of which this is coming from where? 5 by 2 coming from where? Let us say. I will tell us. I use 5 by 2 coming from where? But the term 5 by 2 coming From which contributions? Which contributions? Transition rotation. And this is vibrational factor. Quantized. Is okay though? The total. For one molecule and for, then if you want to for 1 mole, what is the answer? R 5/2 plus, I just repeat. Right here, where once more, U is H nu by kT. What is nu? Nu is the frequency of vibration. I told you once before, K is the, H nu by kT. H is the Planck's constant. Planck's constant. What is this value? 6.624 10 to the power minus 34 joule second is equal to this. Okay, very good. Easily. Happy. Okay, very good. So this is this now for right. This is for what? For how many? 1 mole means 1 gram mole. Okay, these two expressions I have given you. Remove this. And K is the Boltzmann constant. Boltzmann constant, okay, double n perhaps, no? Constant, okay, is R by n. No, this is fine. Okay, very good. So now what is this? That's it. Consider now two cases. Achha. Come on. For light molecules, cases. For light molecules, like hydrogen, HCl. Frequency of vibration for being light, frequency of vibration is large. Nu is large, and hence U large. Oh, this U large. What happens when it is large? Follow me. Then CB is what? CB is approximately, first term is, second term is what? Approximately R times 5/2. Please tell me what is this? Follow. U is a large, denominator is a large quantity and squared. This is also large, but this is squared. This is also square, but this is linear. It means quadratic, square. And you cannot compare with exponential. We have taken an example. 9 square and e to the power 9. Have you checked this? 9 square is nearly 81. Is 81, and e to the power means 2 to the power 9 or 3 to the power 2.7, etc. If you consider 2 to the power 9, how 2 to the 5 is already, so you will get actually large quantity. So the large, this square and this square is large. So this is totally, this term is very small. Because denominator is very large, so this term is small. So we can write plus approximately. We consider when it is large, denominator large means the whole thing is small. So 10 into 0. So what remains? This gives you 5/2R for light molecules. For heavy molecules, for light molecules, heavy molecules, example, iodine, bromine, chlorine. Nu is what? Nu is small, being heavy. Nu frequency of vibration is small, and hence U small. And so small, we actually idealize this as if very small, so that U tends to, this we do when small, make it extremely small so that it tends to 0. When it is tending to 0, you have to answer this. I'm writing CB. I'm once more writing R. Copying from this, for 1 more. I'm writing 5/2 plus, see, limit. You tell me, can you tell me? I'm writing for you. u tends to 0, what is the value of this limit? This is very interesting exercise for you in limit and continuity. Remember, in limit class, this is everything is required. I help you. I help you. Coming time, okay? Yeah, you must be, okay? Abes, Barakpur, local, late today. Ask them, okay? Agitate there. Instead of coming here, agitate there to be in time. No point coming here so late. So, so what is this? Limit h tends to 0. Recall rule help you. Limit h tends to 0. E to the power h minus 1 by h is what? You know, the standard limit is what? What? You don't know. Limit is just 1, pure 1. Oh, h by e to the h minus 1. This is what? So you consider this is the h. U is h, e to the h. This one. So follow me. E to the power h minus 1 by h and whole thing is squared. So 1 squared. So 1 and u is tending to 0 means e to the power 0 is 1. The whole thing is 1. Whole thing is 1. As defined from 0 means now significant contribution coming 1. So can I write this? Shall I write here? Or shall I write here or maybe above? Maybe above. Maybe above here. Let me write. R is 5 by 2 plus 1. Okay. E to the power 0 is 1 right here. E to the power. Okay. You go this one. 1 square. 1. How to get this? Okay. Yeah. This is so easy. Is 7 by 2 R. 7 by 2 R. Happy? Okay. 5 by 2 plus 1. So there is vibrational contribution. Vibrational heat capacity. This one R is vibrational heat capacity. Others are translation and rotational. This is applicable where? For heavy molecules. For light molecules, this is small. So this is the one. So actually, I will actually take back this later on. Right, I'm writing here, maybe helpful. This will be little later. This I'm just copying. This I'm copying for later discussion. It will help you. For some reasons, okay? I'll discuss, I'll tell you. Okay, let's save this. Save this for later discussion. Remove, always remove all this. Okay, so remove this. Remove this. So what you are getting? So monatomic. What is the? Oh no, monatomic already over. Diatomic. Sorry. Diatomic. Light molecules. Light molecules. Okay. Diatomic. Okay, it is unnecessary. You write this way. Diatomic light molecules. Light molecules. What is the light molecule like? You see, tell me. What is the Cb? Please tell me. Cb is a moment ago 5 by 2 R. Molar. 1 mole. Molar. And Cp is what? If Cb is 5 by 2 R, we can use the relation for ideal gas is 7 by 2 R. Cp minus Cb is R. Noting Cp minus Cb is 5 by 2 R. Cb plus R is 7 by 2 R. Over. Wow. Okay, 7 by 2 R. If you want to know what is this in calorie, R is about 1.98 calorie. Means 2, roughly 2. So it is 7 calorie. Approximately 7 calorie. Or if R is in joule, how much? Hello, what are you doing there? What is the value of R? Okay, what are you doing there? No. Here, concentrate here. So 8. 8 means 4, 28, roughly. About 28 joule. Roughly, Okay, hell. So this is about what? Line molecules. Line B. Okay, line molecules. Okay. Eg, light, Eg, hydrogen, HCl. Heavy molecules. Heavy molecules. Eg, bromine, iodine, etc. So what is Cb? Tell me a moment ago. 7 by, a moment ago, yes, standing here, yeah, right there, at the sticking right at the 7 by 2 r, hence Cp must be 9 by 2 r. Oh, another thing I forgot, this is easy to follow. For monatomic note, no, this okay. Cp by Cv is then, hence for this Cp by Cv, this is actually purple. Like molecule, Cp by Cv is what? Tell me, 7 by 1.4, okay, 1.4. And monatomic, note for monatomic, here right. For monatomic ideal gases, Cp by Cv is so easy. What I said, give you Cp value is 3 by 2, 5 by 3, 5 by 3, Cp by Cv, 5 by 2, 5 by 2 r and 3 by 2 r, 5 by 3. Because Cp by Cv, which is known as gamma. Gamma, where is gamma? This is gamma, is Cp by Cv. Cp by Cv is what? Cv is 3 by 2, 5 by 2. So 5 by 3. Roughly, yes, this is additional noting, okay? So this is over. So I will sketch this one, this result. This result I will sketch you, remember this, Cp is for this and for this, just now, okay, remember. For monatomic and diatomic with the sketch. So can I remove this? I am removing all this. I think you have already. Already actually. It's better I actually, can I remove this? Okay, very good. Very good. So this have a sketch, the heat capacities. Cp, you know, unit joule, molar, joule per mole. The question is okay. Log T to accommodate a large range of temperature. That's why I use log. Okay. So 1 to 1000, say 100 to 1000 you want to accommodate, this log of 100 is 2 only, 1000 3 only, so very easy. So or say 10 to the 4, 10 to the 5, 5. So in 1 to 5 we can accommodate 10 to the 5. So that's why log T is used. Or maybe directly some relations involve log, then of course you use substitute. You will plot. So here log T. What is this? I tell you, log T is what? 2.3, maybe 3, maybe 3.3. This means what temperature it is? Log T. Log T 2 means it is actually, tell me, 200 Kelvin. You know, log 2 is 0.3. Log 100 is 2. So 2.3 is 100, okay, times 2, actually 200. This is what, tell me, it is right here, this is right here, T is. This is log T, this is T is what? Right, I am writing here. T is, tell me, 1000. Log 1000 is what? 3000 Kelvin. And this is obviously similarly 2000. Corresponding values, just for your appreciation of the temperature. Now, I am sketching what I am sketching here. So this is what value, I tell you what, this is your 0. This is your, what is that called, or what is the Cp, light molecules? Tell me, light molecules, a moment ago I have given you 7 by 2, 7 by 2 r. Cp. 7 by 2 r. 7 by 2 r means, I am writing 7 by 2 r, you know what is the meaning of this? This is 7 by 2 r. If calorie, then 7 calorie or 28 joule, okay? And this is your, say, 9 by 2 r. This is a scale. So this is happening actually, I tell you what, you know, what is this? Bromine is what? 9 by 2 r, okay? 9 by 2 r, when it is actually, but if you consider temperature effect, the U is H nu by kT, so it will be like this. But when temperature, okay, decreases, this will fall. Because there is actually temperature effect in the exponential term, okay, quantized term. So this is your one, what is this called? Maybe bromine, okay, iodine. Bromine. This is bromine. Maybe chlorine. This decreases. And in fact, okay, so this is iodine. And it is, suppose you consider this is your light molecules, typically light, hydrogen, but there is also deviation at high temperature slightly increases, slightly, and here for hydrogen particularly there is a fall, slight fall. This is hydrogen, this is actually H2SO7, particularly for hydrogen. Okay, so this is the sketch. Okay, I will give you a handout on this. Handout will be from, I told you yesterday, remember, from whose book? Lewis and Randall Thermodynamics. And Lewis and Randall later edited. This I will give you not today, next class. Okay, so this is your sketch of this heat capacity. Now we will take up heat capacity of solids. Heat capacity of solids. Okay, gases over, ideal gas over. Solids is what you know. What do you? Dulong and Petit. What comes in your mind when heat capacity of solid? Whose name? Dulong and Petit. You know, Dulong and Petit's empirical observation. Empirical relation is what? You know, Cv is 3R for all solids, for most solids, maybe more defensive. For most solids, Cv is 3R. Remember, 3R. Solids I am discussing. Solids actually 3R. This was supported at high temperatures, but the relation fails at low temperature. This is the problem. I will show you. This is okay. This is the one. Removing this. This is the picture. This is the Cv. Empirical money, you know what is empirical? Empirical means experience. Experiment, experience from studies. Not, that means as different from theoretical. No theory here. No theory. Okay, so from experience, empirical means, okay. So, but the relation fails at low temperatures, okay, at low temperatures, okay. So, this, for example, this is the figure, I will show you, this is your 3R, and Cv, this is your 0. Again, it's a log T in this scale, 1, 2, 3. What is the like air? This is supported, very good. This is supported 3R supported. Then in what is this temperature? 100, even a little earlier, maybe just maybe this is. So this drastic fall at low temperature from 3R. This is 3R. 3R line. So how to explain this? This could not be explained. This was explained by quantum mechanics. And who did this? You know, Einstein. Einstein first took up this challenge and said, explain the heat capacity. Okay, the decreasing heat capacity with temperature at low temperatures. Okay. This behavior was explained by Einstein. So, Einstein question is, what is why the temperature, why the heat capacity Cv, why do the Cv values drastically drop at low temperatures. Remember, no answer from classical mechanics. Is Dulong Petit or Indian? No answer. No answer from classical mechanics. Classical mechanics means Newtonian mechanics, you may consider. No answer. However, explained by, however, answer given by using quantum mechanics. Quantum mechanics. And this is considered the early terms, one of the early terms, victories of quantum theory. And quantum theory was actually started to be accepted. For this credit. So there are many doubts about this. There had been many doubts, but those doubters actually gradually began to concede, began to accept quantum theory because of this explanation. So this is one of the early terms of quantum theory. So remember, one of the so this is actually now who solved this? This was done by Einstein. This was accepted. This was resolved by. This was done by Einstein. What Einstein did? Einstein. This is year 1907, maybe 1907, and Dulong Petit maybe. I'm not very sure, close to 1800. Okay, so 1907, what he said, he considered solids are actually harmonic oscillators. Solid atoms behave like harmonic oscillators. Now can I remove this? I remove all these things, okay? So I will follow Einstein. So solids, you see, so this is one solid, consider crystal atom. So and there is another in the neighborhood, and still another on the left hand side and right hand side. It is vibrating towards this oscillation. This vibration is actually in the fashion, in the manner of simple harmonic motion. Harmonic oscillator. Okay. Why it is vibrating? Remember what is the simple harmonic motion? Okay. What it follows Hooke's law. When the vibration follows Hooke's law, then it executes simple harmonic motion. What is the Hooke's law? Now, when it tries to move away from this position, central position moves away, then restraining force increases also. That means it cannot go past a limit, a maximum value. Then it cannot go beyond that because restraining force also has increased. Like pendulum, just a pendulum. Pendulum, it swings swings. When it goes there, restraining force maximum. So it cannot go further. Comes here actually restraining force is 0. Is proportional to the distance, restraining force. Increases. When there is no displacement, maximum restraining force is also 0. And also, when the movement is in this direction, restraining force in the opposite direction. So, this is the property, Hooke's law. And these atoms vibrate in this manner. Okay. So when it goes, it tries to there, then restraining force wants to bring it back to its position. Then again this side. There are attractions between atoms. Atoms have attraction. So the ideal gas attraction starts from when? Non-ideal gas. Attraction between atoms start, okay, consider when in non-ideal gas, then liquid and more and maximum in solids. This is actually the ideal gas, no attraction. But non-ideal system, there is attraction between molecules. So there is attraction. Here attraction, okay. So this results the vibration, but this vibration, since it is attracted here, but restraining force tries to bring it back. So it executes simple harmonic motion. Harmonic oscillator, we say. If this is so, what is this vibration of the bromine gas, ideal gas, bromine molecule? They're similar. Bromine molecule, bromine or hydrogen molecule. You remember this? What happens? There are two atoms. What is the mode? This and this vibrating. A similar thing. Okay. So this is moving this way, and that is another one. Okay? This is this way and this way. Okay, sorry. So vibration this way. Okay. Now this way, see, this goes, then this likewise, this vibration. Okay. So we already consider the energy, heat capacity. Follow this vibration. They are also so between the two molecules. Okay, vibration. Remember, I told you what? Remember what? This. Give this. When the same direction, this is translation. Same direction, both same direction, translation. One mode of translation. Other two already there, three. But when this is this and this is this, in this case it is vibration, in the other case it is rotation. This I said. So this is possible, or another is this and this is possible also. You are going this way. One is this way, another is that way. Possible. Another is this way, opposite direction. Vibration. So vibration is actually this type of. So this has a similarity here. So Einstein took up this result here. What is the result? I have saved here. So what is the heat capacity then? So if you follow this simple, this is also simple harmonic motion. Okay. So this is actually harmonic oscillator, and this oscillator, it is history. This is actually after Planck's theory, quantum theory, and when it started to explain black body radiation, history, long history. Okay, we explained this actually. This was introduced. This, what is this? Introduced that forbidden energy gap, and there is actually what is this? And forbidden energy gap, and as I told you, that energies are quantized. And so this is this oscillator, like it was considered actually this oscillator, and this is the energy that I wrote h nu by, this is the energy of each oscillator, vibrating atom. This is the energy of the each oscillator. U, I explained the vibrational, in the vibrational mode. In the black body radiation also, this actually radiation, okay, see the atoms and this makes atoms vibrate, oscillate. So these values are coming from the quantum theory. We started with the explaining of the black body radiation. This value was picked up in the vibration, in the atomic vibrations. Okay, that in the diatomic gas molecule or in the solids. So these values start with this. So start with this Cb. Then so since you consider this, so Cb will be. So this leads to considering Cb is k times u square e to the power u minus 1 squared. Okay, this is this for now you see for one direction. How many directions I have considered? One direction, but this is only one. There is, solids crystals are 3-dimensional. So this is there is another. So it will be this and still another 3-dimensional, but I consider first one dimension. For bromine molecule, how many dimension? This vibration? One bromine molecule, no? Only one vibration, others are rotation. When one is one direction, other is in the opposite direction, it causes rotation in the y axis, and in the x axis, z axis, rotation, 2 rotation and 1 vibration. So one for one dimension, and I used what? K. Note this, K is for how many molecule? One atom. One molecule or atom maybe here. Since solid we use the term atom for one atom. Now what is this? At high temperature, start. At high temperature, tell me, U is what? H nu by kT is high temperature is this tends to this tends to 0. High temperature. Again, idealize high temperature. If it is 0, then what is the limit again? Tell me, what is the limit? This one, remember, high temperature. So U tends to 0 means, remember that one, U tends to 0. So this is 1, this is 1, 1. What remains? CB is K. That is 5 minutes later, 5 minutes. CB is K. CB is K a moment ago. Vibrational contribution is K. So I am taking this up. So for one dimension, one molecule is K. So one right for one dimension, one direction. Stay away from this. Okay, out of my sight. Okay, for one direction and one molecule. For three direction, for one gram atom, molecules which contains n atoms, one atom which contains 1 gram atom, and 3 directions. What is the answer? 1 gram atom contains how many atoms? Avogadro's number. So it is 3 direction, 3 times first of all, and n times next. Easy. I have not done these K is written here. Diatomic bromine K. Vibrational energy. Solid is only vibrational. Oh, solids are only vibrational energy. They don't move around. Then this will not be here. I will not hold it. Okay, if the atoms are moving like this, gas you cannot hold. They are moving around. The solids have only vibrational mode, but gases translation, rotation, vibration. Okay, liquid also vibration. So this solids and gases are easy to explain. Liquid is very complicated things. Okay, but anyway, so 3 direction. So K is already known to you. I have already multiplied for 3 direction 3K, and for 1 gram atom system which contains Avogadro's number of atoms. One n is Avogadro's number. You understand Avogadro's number. So 3nk. What is this? 3nk. K times n is what? 3. A moment ago. K is what? R by n. Boltzmann constant is R by n. K is R by n. Okay. What is this? No, this is okay. K is R by n. R by n. So what you get? So reconciled. So it is happy reconciled. Come in. Reconciled. So but the question remains, why is our decreasing temperature? Why the heat capacity drastically drops? This will be explained. At high temperature, at low temperature, don't use this. At low temperature, for example, you do this, you can do yourself. Why it is decreasing drastically to almost negligible value? You can do this. Use temperature, high temperature 0, low temperature, this will be very large quantity. Large quantity, again that thing is coming. Denominator large means tending to 0. So CB tending to 0 falls to this figure I just now removed, falls to 0 at low temperature. This was not explained by the Dulong-Petit's empirical relation, empirical findings, or any classical theory. Classical theory, someone actually showed this theoretically, but this cannot explain this part. This is only due to quantum mechanics. This goes to the credit of quantum mechanics. This drop. Remember, this figure always inscribed. This is quantum mechanics explanation. So this is okay. This part. Next is now this. Now what happens? Let us now sketch this. How I am once more drawing this. So remove all this. Once more drawing what I removed. Once more. This is helpful. Oh, this is helpful. I am drawing once more. I say for aluminum, for example. Let us see how is Einstein result successful. How much is successful? CB. You have note CB I am writing. CB. CB, this is T again, log T. Again 1, 2, that same scale, 3. This is actually typical figure. This is 3R, your famous 3R for solid reference. Then this is the figure. Is 100 though? This is the figure. See, when temperature tending to low temperature tending to U is very large and denominator is very large, so 0. This is 0 value. So this is the finding. This is the experimental. Einstein is where? Einstein not exactly there. This is Einstein result. Einstein result. This is experimental. This is data, experimental data. So there is a difference. There is actually a drift. So this was explained by whom? This discrepancy was explained by Debye. Einstein disciple maybe. So by Debye. So next Debye explained 19 what? This is 1907, maybe 19 approximately 1915 maybe. Debye explained the mismatch between experimental observation on CB and Einstein results. Theoretical calculations. Debye did what? Oh, one thing I forgot to tell, note, I forgot. Einstein considered all atoms have the single frequency. The frequency has a nu or single frequency, same frequency. All atoms in a crystal, they vibrate with the single frequency, same frequency, nu. But Debye said, so Einstein considered same frequency, same and single frequency for all oscillators. Oscillators means what? Who are oscillators? Atoms. But Debye considered a spectrum of frequency. That is interesting. Debye considered a spectrum of frequency. This is the main difference, and this is more involved. Debye, I am not actually considering the details. Debye. So what is this? Now then again another way you can consider this. Why single frequency? Why Einstein considered single frequency? Because Einstein considered all atoms vibrate. Remember, I am talking of vibrational. Solids mean vibrational. All atoms vibrate, okay, independently of one another. While and Debye independent, so same frequency, same frequency, and here all atoms vibrate dependently. So what is the result? Single frequency. What is the result here? No. Tomorrow. Single frequency, and this is again dependently on one another. What is the result? Multiple frequency. Spectrum facts. Multiple frequency. Very good. Multiple frequency. This is result. So I will go. Okay. Let me finish divide. So divide findings. Divide findings. I cannot give you the details of divide theoretical treatment, but I give you the result. I'll give you a handout on this, so you may consult. Divide result. What is the result? Sorry, quickly. I don't have much time left. This is the result. What is this? Divide result is for low temperatures. So problem with the low temperature. Remember what? See, 3 hours. High temperature 3 hours. 3 hours. 3 hours. 3 hours. No problem. Dulong Petit, very good. Low temperature problem. Quantum mechanics. So divide result is for low temperatures. At low temperatures, CV is 2 hours approximately, maybe pi to the power 4 R by 5 T by theta D. D for divide. Theta D. Q. Remember this. TQ. Q. Fortunately, okay. Power I missed actually. So this is actually approximately is constant times TQ. So it changes with the third power of temperature. So this is the CV at low temperature, underline, at low temperature regime. Means what is the regime? Say maybe 100 Kelvin, 200 Kelvin. This is the domain. We're talking drastic fall. So this is the answer. So then what is theta D? I said D by temperature maybe, just if I remember, D by temperature. It is temperature, that is temperature, both are temperature, okay? Unit of interesting. In temperature, no unit, no dimension. 12, 5, pi, no dimension. So these must have the same dimension as R. It is practically so. R is what? R is what? Joule per mole per Kelvin. And molar heat capacity, joule per mole per Kelvin. No surprise. So dimensionally consistent result in casing. Very good. D by temperature is what? H nu D by K. What is nu D? Is the maximum frequency D by frequency, maybe you call D by frequency. D by frequency in the distribution of frequencies. Maximum value, which is H nu D by K, okay, theta D. If you ask me theta D further, theta D increases, this additional, theta D increases with as rigidity increases. Rigidity of crystal. Let me write here. Here, quickly. Let's finish this part. So theta D, note. Theta D increases as rigidity of the crystal, that is increases. That is as interatomic force, or as bond energy rather, as bond energy increases. High value, okay. And what is this? And theta D decreases as atomic mass increases. This is easy to follow. Why atomic mass means? A moment ago, heavy molecule, low frequency, and theta D is what? There is a frequency here. Is new frequency. Nu decreases, heavy molecule, theta d decreases. And this is rigidity example, e.g., okay, diamond. Large cohesive force. Okay, the interatomic force in diamond large. And in, what is example? Example I will tell you, e.g., lead. Lead is heavy atom. So what is the atomic weight? Lead 207. So heavy. So e.g. for lead, theta d small. Write this. Theta, this is better way of writing. E.g. for diamond. Diamond is a covalent bond, very strong bond. Diamond. So strong interatomic force, binding energy, and cohesive force, rigidity. So for diamond, tell me theta d. Tell me theta d. Theta d large. So right here, theta d large. This is the message. Now quickly I give you the last drawing. Okay, I am almost over. Actually, but it is not. Quickly, this one, this observation. Observation. CV log t quickly. Okay, same deal. 1, 2, 3. Again, you know what is this? What is the limit here? This 3 r. So do yourself. Okay. So lead is what? This is lead. What is the theta d? Lead theta d? 90 say. 90. I mean approximately because I buy 90. 90 temperatures Kelvin actually, Kelvin. And then what is next is silver. Then aluminum. And here little further away is who? Remember all decreasing temperature, that is from this H nu by kT relation, you will get that. But the thing is this, at a given temperature, this is CV is least because what you have got this, theta d decreases, theta d increases. What's the theta d here? Tell me. Oh, 1900. Sorry. 1900. Silver 200. Sorry, silver theta d is 190. I'll give you a handout on this. Aluminum is theta d is about 400. 400 Kelvin. This is Kelvin actually, theta d is Kelvin. Temperature Kelvin. This I wanted to tell about the heat capacity of solids. And this is over. Then next class I will consider electronic heat capacity and remaining part the heat capacity of non-ideal gas and liquids. Thank you very much. With these words, actually we have concluded our